Hello, this video will cover page 3 of section 5.2 notes. This includes two formulas and examples 5 and 6. So since the binomial variable is a probability distribution, that means it should have an expected value and a standard deviation. The expected value of a binomial variable, so remember if it's binomial, that means x is binomial n comma p. Well, then the expected value of x actually will just be n times p. You just multiply them together, which that kind of makes sense. If you're interviewing 10 people and on average 30% of the people have the probability you're looking for, that means the expected number of people out of 10 would be 3, because 10 times 0.3 is 3. Now the standard deviation, a little bit more difficult to explain, but it's the square root of n times p times 1 minus p. Now you will be given these formulas on the exam, but just the formulas. I'm not going to call it like expected value of a binomial variable. I'm just going to say e of x equals np. Okay. So using these two formulas, we can do examples 5 and 6. In an actual experiment, Mendel generated 580 offspring peas. He claimed that 75% of them would have green pods. The actual experiment resulted in 428 peas with green pods. Is this unusual? So to figure out if this was unusual, you could try to see what's the probability that x is less than or equal to 428. Yeah, that's what I want. And that'll give you how unusual 428 is. But as you have noticed, I'm hoping, this would take a lot of time, because you would have to calculate about 428 different probabilities. You could do the complement rule, but you would still have about 160 to calculate. So we're not going to do that method. Instead, we're going to use some estimation using the expected value and standard deviation. So the expected value, I forgot to write over here, x is binomial 580, and not from x is binomial 580 comma 0.75. So the expected value would just be 580 times 0.75, which is 435. And since 428 is close to 435, I would say that this is not unusual. But to determine how close is close enough, that's where the standard deviation comes in. Because remember, the standard deviation measures how far spread out the data is. So if the data is very spread out, 435 makes sense. But if the data is not spread out at all, like the standard deviation is only 2, 428 would actually be unusual. Because if you go 2 away from 435, that only gets you a 433, which is larger than 428. But anyways, let's calculate what the standard deviation is. So the square root of 580 times 0.75 times 1 minus 0.75, which is 10.43. So definitely, if I go one standard deviation below the mean, we get 435 minus 10.43, which is 424.57. So that definitely includes the 428. And you don't always check one standard deviation below the mean. A general rule of thumb is about 95% of the data falls within 2 standard deviations from the mean. So 2 standard deviations below or above. So if 1 didn't work, I would check 2 next. But if it's further than 2 away, then yes, it would be unusual. Not impossible, just unusual. So is this unusual? No, this is not unusual. Poor transition there. Example 6. If 40 individuals were randomly selected to participate in the Milgram's experiment, how many individuals would be expected to refuse to administer the worst shock? And then what's the standard deviation? So this would be X is been 40, comma. I need to go back up because I already forgot what P was. P was 0.3. So 0.3. The expected value then is 40 times 0.3, which is 12. And then the standard deviation is the square root of 40 times 0.3 times 1 minus 0.3. Which is 2.9. And that's it for section 5.2.